Well, how do you do, people? The way that we are going to do our kind of pre-lab prep is watching these videos. So essentially, I'm going to be making these videos as, if you think about your introductory physics labs, the way they normally run is, there are, physics majors may be a little bit different, but in general, there's, 20-ish of you in the second floor of Mendel in the big kind of lab rooms. And, the professor will do some introduction to the topic at hand, show you how the experiment runs. And for us, if you check out the syllabus, which I will make another video on, no worries. We'll talk about it the first day. We will, I like to do a similar type of thing with the syllabus day because if I record it and send the recording to you, you can go back and watch it. And I'm gonna go, line by line through the syllabus to tell you everything, So it really isn't super fun to be doing that in every single class on the first week. At least I didn't feel that it was particularly useful in college. So that's something I like to do. So I'll supply that as well. But if you notice, in the syllabus, it has these, what we're doing each particular week. And you'll notice a lot of the times it has two labs listed. That's because we only have one setup for all of these labs. We only have one setup. So, that could kind of be feasible in one of our sections, which has 5 students, but seven, a little bit much. So what we'll normally be doing is splitting the class into two separate lab experiments. So instead of me giving two 20-minute intros to people who are half listening, half trying to understand what they're doing, this is going to be something that's on you. You watch these videos prior to coming to class. Obviously, if you have questions, my entire job as the lab professor is to help you succeed and ask questions and troubleshoot and all sorts of things like that. If you don't understand a particular aspect of the theory, go for it, ask, and we will just go through the entire, the phenomena of what we're seeing, or the theory behind the phenomena of what we're particularly working with that week. So that's the normal way, except the very first week. The very first week, both lab groups will be doing a lab. It is a very, very light lab. So light, in fact, that this video, even if, let's say, Professor Brown last year did a similar thing that I did, right? He recorded these videos prior to you coming in. He wouldn't have done it for lab one. His methodology for this first lab, which I love, I just thought, coming straight out of summer break, and quite frankly, the last thing you guys took to prep for this course was modern physics, and at least my experience with modern physics was way beyond this particular. It's called the diffraction grating technically because we are using a diffraction grating, but it is the double slit experiment effectively. And I didn't really remember doing much of that in modern physics. That was like intro level stuff. So I just wanted to kind of prep you guys, give you a little bit of the theory, show you how I did it, because effectively the way that this was done in the past was just you'd walk in, you'd do your whole syllabus spiel for the first day, and then Professor Brown would hand you a laser and one of these and say, with a piece of tape across the wavelength of this laser and say, tell me what the wavelength of the laser is. And you can't leave until you do. So I thought it would be a little bit good, like first training steps to do a very easy lab like this, but not to make it due before you leave, but rather stick to the same schedule. So like everyone, for instance, will be doing a diffraction grating report on this first lab, which I think is perfect because we meet for lab on our first day, and then we have labor break. Labor Day break. So one, it's the first lab report, so it will be graded incredibly leniently. And two, you have 2 weeks to do it instead of the normal 1 week. That's not, we'll get there more when we talk in the syllabus, but you do not have just 1 week to do lab in general. You have either 2 or 1, depending on which you pick. You'll see it little bit down here, but I'll get to that in the syllabus video. Okay, so what the heck is this lab all about? Let us, before I get to some of the theory sharing, let me show you a little simulation that we're going to be playing with to kind of guess and check some of these things. So this is a great simulation. This website is called Java Lab. I have been using it to in, a lot of these things, maybe you don't have the Frank Hertz experiment. We do. It's to be able to demo during lecture. So I just pull up this website. It is absolutely incredible. Highly, highly recommend to any physics major just to kind of go through all these things and just see what's going on. They go, some of them quite beyond the introductory level, but most of them stick to that. So what is happening in this experiment? We are shooting light through two slits, and we know that light is both a particle and a wave. That is mentioned. So occasionally in these intro videos, especially I'm going to be doing this one a little bit more, with my own kind of slides that I've used to teach this in the past, because like I said, the way that this was taught previously was hand you this, and go for it. There is no lab manual for this week. So that's a little bit of a weird one about this week. Not a huge difference though, because a lot of the old lab manuals are very, very hard to use as procedure. Some of the theory is very, very tricky. So that's more or less what my job will be every week to make one of these videos so that if I were doing the experiment for the first time, what would I want to know? Essentially, right? That's always what I try to do at the beginning of these like lab theory intros, be it during an introductory class where I'm not doing these videos and I'm just doing it on the fly in the beginning of the room, or how we're doing it now. So occasionally I will be referencing, it's just called Morgan's 3400 textbook. This is a textbook that y'all used for your modern physics. And like I mentioned, it is actually, the double slit is not mentioned very much at all. So I just wanted to remind everyone where this definition derivation comes from. Here it is, very, very small. Double slit experiment, it takes up just a few pages. Modern physics assumes that as something that you touched on in introductory physics. So just for everyone's reference, this is pages 182 in chapter 5 to 184-ish. I believe the end of this example is pretty much it. Okay, so where the heck does that equation come from? Just as I'm sure you all, maybe this is kind of boring to you, but let me really quickly go through it. It turns out that even though modern physics, I'm sure, talked much more about particles, this particular experiment can be discussed entirely with waves. So let's just talk about light as a wave, right? As I shine this laser, I'm not shining it on the camera, that would be silly. It's a wave. And so what is a wave? It is electric fields and magnetic fields intermingling. It turns out we don't really need to think of both of them in this context. We can just think about them as a wave. And in terms of what we see, the phenomena that we see when we look at the double slit experiment is that there are bright and dark fringes. It's not just, if light were a particle that were just a basketball going through two slits, it would just be two marks on the wall, but we're seeing that it's spreading out, something that waves would do. Because if we think about waves as just disturbances in a media, we can just talk about it like water as well. So this constructive and destructive interference where the bright fringes happen, that would be where two waves combine. They're doing the same thing at once and they build on each other, versus they're doing different things and cancel out. So that's something that we can see with just regular old water waves. If we have some kind of disturbance, let's say a little paddle over here, and it's making a wave through the water, if that water hits a slit, it's going to start creating new waves, and not as if it's coming from a paddle, right? You see these kind of longitudinal waves right here, where these are coming out like with spiral symmetry almost. Not almost, just spiral symmetry. That's because it's originating at a point as opposed to just this giant paddle sending these giant waves in there. Now, what happens if we have two of these? Now we've got two different sources for the wave, and at various points, they will constructively interfere or destructively interfere. So let's get a feeling for how that actually happens. We're seeing this kind of, you know, slit interference pattern. So at every single one of these points, it's either going to be constructive interference where the wave is doing the same thing. So if I zoom in here, I'll just give you a little brief preview of what's happening. Notice that the wave is going up, right? So we're going down, up, down, and as it hits the wall, they're both going up. Now, what's happening down here with constructive interference? Let's check out this wave first. Up, down, up, down, up. Now, what is the other wave doing at that moment? Down, up, down. So they're doing different things. So destructive, not a bright fringe. And then the same thing is happening down here. So in terms of what's actually, what needs to be happening at that particular moment, in order for the wave to be doing the same thing, the difference in how long, like let's say the source of the light came over here. And these are all the different, like, let's just say we're using P1 as our kind of baseline. That's the wall. In order for the other waves to constructively interfere with that, they need to be a wavelength longer. So notice what's happening here. Those two paths, they're not the same length because that one, if I were to draw a line, that is a longer distance than that, right? If I think about that as a triangle, the sides of those triangles are going to be different. So that's the first thing we need to start doing is comparing the length of those sides. So in order for something to be doing the same thing, well, that's the definition of a wavelength. After the wave has completed itself and is doing the same thing again, that's how we measure a wavelength. So that's exactly what this definition is telling us, that the two paths, I'm just using this P as path length, these two paths have to be different by a wavelength in order for there to be constructive interference. And now what's the opposite of this? The opposite of this would be if they're doing different things, which would be exactly half a wavelength. So notice what's happening here. Let's just say we're starting measuring right here. Up, down, up, wavelength. And now what would need to happen for this to be doing exactly the opposite thing? It would need to be going down, which happens after half of a wavelength. Because this line right here is half a wavelength. If we were to measure it instead here, that would be the full wavelength that we saw on the previous slide. See, it has an entire wave up, down, up, doing the same thing again. So it begins at half a wavelength of difference. And then if we measure from that location, it's a whole wavelength between those. So this is a little bit of a confusing error. I apologize about that. This one's kind of the more appropriate one to be looking at. So we're starting, okay, half a wavelength. Now it's doing something different. And now a wavelength after that location. So it may actually be a little bit easier to look at this as an equation. If we think about a odd integer, so this could be 1/2 of a wavelength or 3/2 of a wavelength, which would be what? One wavelength and half a wavelength, and so on and so forth. So it's any odd integer like that. So that's where the dark fringes happen. Turns out you can't really measure where the dark fringes happen, so this equation isn't super important. This one's more so the one that we're going to be looking at. But this really doesn't tell us anything about, the thing that we're actually shining through. Like where do these sources come from? They come from these two slits. So that's what we're going to start measuring. We're going to start looking at actually, how do we look at the difference between these two path lengths, not just qualitatively, always get those mixed up, but quantitatively. How do we actually measure the distance between those two things? We know what it needs to be. It needs to be this. They need to differ by a wavelength. But what is the actual distance measured between those two things? So the way that we do that is we make a triangle like I was kind of alluding to before. So if this is the location of the first slit, S1, I've kind of oversaturated this image a little bit. Slit 1, slit 2. The light hits each of these slits and it, spreads out spherically. So we're just analyzing one particular point. Let's just say at that particular point right there, we are seeing either a bright fringe or a dark fringe. This is completely generic. So at the moment, what we're going to do is we are going to draw a line, P1, that'll be the path length that the first wave took from slit 1, and path length 2. Now, how do we measure the difference between those two things? Well, what we can do is notice that this whole path and this whole path, if we were to say that these two things were at the same location, then P1 and P2 would be the same, but they're not. It's got this little extra chunk here. So how do we measure that? Where is this coming from, this d sine theta? Well, if we know how far apart the slits are, for instance, here, distance between the slits, we'll be able to tell what's happening. And we always have that information. Either you've constructed the double slit yourself, or, and we'll talk a little bit more about this in a second, you have a diffraction grating, which tells you right on the bottom how big the slit width is in a little bit of a roundabout way. So we'll get to that in a second. So we know this information, and because this is making a right triangle, we just draw that out to be whatever angle we need to make that a right triangle. Now we can use any kind of trig that we want. So we have the hypotenuse of this, I'm talking about this small triangle now, this one right here. So we have the hypotenuse, there is the right angle. If we're measuring theta by this, and the reason we're using some new random variable theta is because that angle is going to change based on what fringe we're measuring. So if we were measuring this fringe, the angle would be kind of small. If we were measuring that fringe, the angle would be a little bit bigger because we're looking at bigger differences in between these two path lengths. Okay, so at that point, we are looking for, okay, if we're defining that as our angle, that is the opposite side, so we're using the sine function. Hypotenuse, sine function. So now we have an actual quantitative difference between these two path lengths, and now we have two equations for the same quantity. The difference in the path length for the bright fringe was some integer number of wavelengths, and now we know what it is in terms of the actual physical properties of the system. So this is our main equation. This is the one that was kind of just tossed to you in the textbook. They're using n instead of m for integer. No big deal. And that's where that comes from. Okay, so here's the thing. How are we going to use this with our actual system? We don't have a piece of cardboard with two very, very closely placed slits in it. We have a diffraction grating. So what is a diffraction grating? It is effectively the exact same thing, just with a bunch of slits. It is thousands and thousands of parallel slits, and they are doing exactly the exact same thing. There is nothing different than the double slit experiment. The single slit experiment I've removed from this kind of a slide intro. That's a little bit trickier, but the double slit equation gives us the exact same thing as for diffraction, because it's essentially just double slits, but thousands of them instead of just one or two. So obviously two. This equation is going to be what we're using. It is exactly the same as the double slit experiment, but here's a little bit of a something to keep in mind here. Notice on my diffraction grating, it says 300 lines per millimeter. That is not the units that I want in this equation. Let's check the units. That is a wavelength, so meters. M is just an integer, so that means my right-hand side of the equation is meters. Sine theta, just a number, no units. D has to be meters. Is that meters? No, it's lines per millimeter. So what we need to do here is invert this. How many millimeters is one line? That's the only kind of tricky part of setting up the theory of this experiment. Once you got that, it's pretty much a piece of cake. So let me just give you a little bit more simulation stuff. Once, you could also utilize this to check yourself at the end of the day. Don't, if I gave you a blue laser, don't just jump to this and figure out what it is. But you can use your whatever diffraction grating you have. Once you invert it to get the distance between two individual lines, you can use this, see if it matches up with your theory. This one, ignore. This is something that is much more heavy in the optics section. Actually, I believe I pulled this up on YouTube, Wikipedia, just in case. Yes, I did. So if you go to the double slit experiment, this is something that I doubt is even in the modern textbook. You would probably need to go to an optics textbook for this one. It's a different type of diffraction. Here it is. So if the slit width is appreciable compared to the wavelength, so what does appreciable mean? It means same order of magnitude, roughly. So what we're seeing here is, let me make, and this you can really do whatever you want here. This isn't really going to change much of what we're looking at. You notice there's no, you saw earlier in these slides that L was in there, right? But like the distance from your diffraction grating to the wall that you're shining this pattern on it doesn't appear in these equations. However, if you put your diffraction grating very close to the wall, it may be kind of hard to measure. So in that case, you'll see in this picture where I have my setup, it's a little bit far away from the wall. I think I did something on the order of half a meter or something like that. But as long as you can get, I believe that one was the central maximum, and I'm doing 1, 2, 3, 4. So 4 order maxima after that. You can see that kind of listed here. So I would be doing, that's my central maxima, 1, 2, 3, 4. If you can't get that much, that's okay, but at least try to get, 0, 1, 2, 3. Something just so that you don't have a ton of error in your system. And the error, by the way, I'm going to make a whole other video on. I think with each of these labs, at least for the first few weeks, I'm going to be increasing the level of error analysis that we do because, quite frankly, that is the major learning objective of this course. Error analysis and using a computer to actually, do things that you may not have known that you needed to do in intro physics. For instance, normally, you may have done error propagation before. That is certainly something that we'll be doing. And I'll talk about that in the Excel video that's attached to this lab. But there are certain things that Excel cannot do. So there's only, there are limits to the error analysis that you can get done on Excel. So again, that is what my setup looks like. And I'm not really supplying you with any of this stuff. I'm going to do the same. I'm just going to say here, here, and then you guys are going to use some random things around lab. This is not lab. This is where all of the things from 360 have gone while they renovate 360. The floor's done, I think. It looks kind of nice, but there's nothing in there yet. So I haven't moved any of our experiments over there. My office is just cluttered with a multitude of experiments. So just, grab a caliper box, grab your phone, put the laser between it, experiment, do some fun stuff. There's not really much we need to do here. I will say that there is a bit of laser safety here that I want everyone to be aware of. It's not as crazy as it is for some of the other experiments where I talk more at length about laser safety. But I just really want everyone to be careful about lasers in this lab. They are scary to me. Vision loss due to laser is terrifying. This one's not crazy because you don't need to be that far away from the wall. You can be half a meter, and be shining it straight at the wall, and no one needs to go, in front of in front of that laser. Whereas in some other experiments, particularly the speed of light one, which I talk at length about laser safety for that one because there are mirrors which can just shine the laser everywhere. Be diligent. There's no reason to be kind of willy-nilly with any of these things. All the labs are pretty self-contained in that context. We're not going to be doing anything where you need to be troubleshooting with the lasers themselves. I'll be doing all that prior to us getting here. But I'm rambling now. We've got plenty of laser safety in some other videos. Okay, last thing I wanted to do. Oh, just to mention, yeah, what this is all about when it's appreciable to the wavelength. So let's check out, let's just put it at 500 so it's easier to compare, it doesn't really matter. 500 nanometers, if I were to put that in micrometers, is zero point 0.5 micrometers. So if I bring this slit width, which is something that is labeled as B in this equation, it's not even anything that, we've seen. There's no, the distance between these slits was never mentioned to us. I'm sorry, the width of those slits was never mentioned to us, only the distance in between them. So if we were to make that number on par with something like half a micrometer, put it even, can I make it higher? No, that's just hard to see. No, just keep it like that. So if I make this very, very small, like, okay, it goes down to 1 micrometer. Is there any way for me to make this easier to see? Like that. So that's where you're seeing it's kind of there's not a ton of central maxima saturation anymore because that is now 1 micrometer and the wavelength itself is half a micrometer. So it's going through things that it can't there's not enough room for constructive interference because it's just, that effectively what we're saying here is the wavelength of the object is half a micrometer, and the slit width it's going through is 1 micrometer. So it doesn't have as many options as if it were that big and the slit was that big. Then it could, it has all that room to move around. If you make the object bigger or the slit smaller or bigger, there's a little bit weirder stuff going on. So like I said, if I look at this reference, I'm sure, yes, it's an optics textbook. So it's not something that we need to worry about. All right, let's see. Is there anything else in here? I think that's it. All right, y'all, enjoy. I will be creating an Excel video for us to talk about how we're going to be doing error for this lab because it's a little bit tricky. Once we get this data, what are we plotting? Obviously, we want to figure out what the wavelength is. That's going to be taped over. We don't know what it is. So our objective is finding out what lambda is. We know what D is. We'll be able to measure what this theta is, and we'll figure out what M is. So the way effectively, I think I'll just save that for the Excel video instead of, kind of bombarding this. I've already been rambling for too long.